So, we would continue with our discussion on internal flow. Yesterday what we have seen is that internal flow, it is difficult to define what is a thermally fully developed flow. For the case of hydrodynamically fully developed flow, we understand that the axial velocity, if we denote it as Vx, is a function of r, but it is not going to be a function of z. So, any profile which is set in a flowing fluid through a tube, the shape of the profile will not change and the values of the velocity at any fixed location, at any fixed r location will not change. To give you an example, we understand that in laminar flow through a pipe, once the flow is fully developed, that means once the developing boundary layers from the surface, inner surface of the tube coincide and meet at a certain point along the axis from the center, that distance is known as the entry length. But beyond that entry length, which is a function of Reynolds number, but beyond that entry length, the velocity profile for laminar flow will remain parabolic. Not only that, let us say we are trying to find out what is the velocity at r by 2, that is in between the center line and the inner surface of the tube, which is denoted by r, small r equals capital R by 2. So, if we can measure the velocity at that specific location, and once the flow is fully developed, that number, that velocity will remain unchanged with axial position. So, the shape will remain parabolic and the individual values of the point velocity will remain same as long as my r, that is the distance from the center line, remains same. So, we have also seen that how this entrance length can be expressed as a function of Reynolds number, what would be the case for turbulent flow and what would be the case for laminar flow. But in both flows, the independence of the axial velocity with axial position is the hallmark of hydrodynamically fully developed flow. But the situation is more complicated for the case of thermally fully developed flow, because since either let us say the tube wall is maintained at a constant temperature or a constant heat flux is being applied to the outside of the tube and the fluid is flowing through the tube. Now, when the fluid flows, since it is gaining energy because of either the elevated temperature or the applied heat flux, the temperature will vary with axial position. So, the question then comes, how do we define thermally fully developed flow? If you remember, like there were two criteria which were to be met if it is hydrodynamically fully developed. One is the axial, the independence of the velocity with axial position, and second, the shape of the profile will remain unchanged. So, for the case of thermally fully developed flow, we revert to the second. We say that the dimensionless temperature profile will not change with axial position, but we understand that the temperature at even at any given r location will vary with position as long as I have a constant surface temperature or a constant heat, as long as the fluid is receiving energy from the side walls due to a heat flux or due to an elevated temperature. So, we do not talk about the individual values anymore. What we say is that dimensionless profile shape will not be a function of location. So, that is why we use the expression del x of a dimensionless temperature profile is equal to 0. And since the dimensionless temperature profile is not a function of r, so we can take the so not a function of r. So, if you take del r of that dimensionless number, it is also going to be independent of r, and therefore, we have obtained certain relations. The most important one which characterizes the thermally fully developed flow is that we found that the heat transfer coefficient, the convective heat transfer coefficient in the thermally fully developed zone is independent of axial position. So, if you think of the entrance length, there the heat transfer coefficient is a function of x, but once you go beyond that thermal entry length, which of course is different for whether the flow is laminar or whether the flow is turbulent, but once you cross that thermal entry length, the h is not going to be a function of position, function of axial position. So, that is what we have seen in yesterday's class. We have also defined certain the Tm, the mean temperature of the fluid, and we have obtained the mean temperature of fluid by considering the total of amount of energy which is flowing in a cross section. In this, the calculation of the heat total energy which is flowing through a cross section gave us the definition of the mean temperature, which was denoted as Tm. So, in order to calculate Tm, we calculated the total energy. So, it is going to be integration of the velocity, which is a function of r, integration of times u, which is again a function of r, times Cv, rho, and so on, such that when once integrated, it would be of the form of mCp delta T. So, this is how we have defined the temperature. What we are going to do in today's class is pick two ideal cases, two limiting cases. In one case, the heat flux is going to remain a constant. That means, the surface is going to receive, the inner surface is going to receive a fixed quantity of heat flux remaining constant, and in the second case, the temperature of the tube will be kept constant. So, in the first case, as we understand, in order to drive the same amount of heat to the fluid from the walls of the tube, the heat flux will change, the heat flux will remain, and the heat flux is identical. So, therefore, the temperature will keep on changing. Okay. As the fluid flows in the tube, its mean temperature will increase, and if its mean temperature is increasing, then in order to drive the same quantity of heat to the fluid, the temperature of the tube surface will also increase. In other words, the Ts, which is the surface temperature of the tube, will keep on changing with x. In this, and which can be very easily obtained by just wrapping a heater, a strip heater around the tube, and to ensure that a constant power is being provided by the strip heater to the flowing fluid through the tube walls. The other condition is that the surface temperature of the tube is kept constant, which is a very common occurrence when, let us say, steam, the saturated steam is condensing on the outer wall of the tube. So, when the saturated steam at a certain pressure is condensing, then it's going to be at a specific temperature. So, a condensing steam on the outside of the surface is a perfect example of the temperature being kept constant while the flow is taking place. So, we will look into these two, and our aim is to obtain ultimately from an engineering standpoint, can we use the science, can we use our understanding to obtain an expression of H, the convective heat transfer coefficient for flow inside a tube. That is our goal, and we would like to see what would be the value of H when we have either a constant surface heat flux condition or a constant temperature condition. So, these are the two cases in which you would see that the heat transfer coefficient, the value of the heat transfer coefficient is constant, and not only constant, the Nusselt number will just be equal to a numerical value. So, the heat transfer coefficient H d by k, that is the Nusselt number, will have specific constant value based on whether you have constant heat flux or constant surface temperature. So, we would start the analysis, but in order to do that, the first thing that we would do is we are going to start with uniform surface heat flux, and I am restricting to thermally fully developed flow, and which means not only Qs is constant, my H is also constant as I have expressed before. Okay. So, for completeness, if I plot the value of H and if I plot it with axial position, the profile would the qualitative nature of the profile would be like this, where this point from where the H is more or less, H is not a function of x in this region, which is it is a constant. So, this is H f d, the heat transfer coefficient for fully developed flow, and the x for which this happens is x f d, that is the entrance length for fully developed flow. So, this is how it would behave. So, for the case of uniform surface heat flux, both H and Qs are constant, and the Newton's law would give me would connect the constant heat flux with H times Ts minus Tm. Okay. So, since both these two are constant, then I can simply write dTs by dx should be equal to dTm by dx. We realize that Ts is the surface temperature, which for the case of uniform surface heat flux is going to change with x, and Tm being the area averaged mean temperature based on energy consideration, it is obviously not a function of r, but it will also change with x. So, as the fluid progresses more and more into the tube, the Tm will be different, and if it is a heat flux which is being added to the fluid, then Tm will increase with x. So, we will start with the definition of thermally fully developed flow, which is Ts, which in this case is a function of x, minus the temperature at any point, which would be a function of r and x, divided by Ts, a function of x, minus Tm, which is the mean temperature, also a function of x. This is going to be equal to 0. So, if you solve for del T del x from here, what you get for del T del x is dTs by dx, this being a function of x only, so it is simply an expansion of this one. So, it is a simple derivative, taking the derivative to trying to find out what is del T del x. Now, for Qs to be constant, if Qs is constant, dTx dx is equal to dTm dx. So, if you look at these two terms, since these two are identical, these two are equal, then these two terms therefore can be cancelled. So, these two terms will be cancelled, and what you get is del T by del x is equal to dTm by dx for Q double prime s to be a constant. So, if you have a constant surface condition, then the variation, the axial temperature gradient, is going to be independent of the radial location. If you look carefully once again, this T is a function of r and x, but when it is fully developed and for the case of Q double prime s to be constant, the gradient in the temperature is going to be independent of the radial location, since your dTm dx is not a function of r. So, that is the main conclusion that you can derive simply considering the constancy of x, Newton's law, which gives this relation, use the definition of thermally fully developed flow, expand it, cancel the terms since these two are equal, and what you get is the actual temperature gradient is independent of the radial location. So, the conclusion from this is axial temperature gradient is independent of radial location. That is a very important important statement which we are going to use later on. So, since we have done it for uniform surface heat flux for the case of thermally fully developed flow, we must also look at what happens when it is constant surface temperature. So, the second case is for constant surface temperature. What would be the statement, what would be the profile, what can we say about the profile? Since it is a constant surface temperature, so dTs dx would be equal to 0, okay, as Ts is constant. So, if you look at this profile, if you look at this in the expression that we have obtained by solving from the definition of fully developed flow del T del x. So, this is going to be 0 since dTx dx is 0, this is going to be 0 as well. So, what we would have del T del x is simply going to be this one. So, we can write the del T del x T s minus T divided by T s minus T m times dt m by dx. Now, if you look carefully into this expression, what we have obtained in here is that the actual temperature gradient is now going to be a function of radial coordinate as well, because the T that you have here, the temperature of the fluid is a function of radial position as well as it is a function of axial position. So, Ts is a constant in this case. This is so these Ts's are constant. Tm does not depend on r, it only depends on x, but because of the appearance of T in the expression of del T del x, for constant surface temperature, the del T del x depends on the radial coordinate as well. So, that is the difference what we would get in terms of the fully developed flow for constant surface heat flux condition, and for the case where the temperature is kept constant. Now, we are going to probe a bit further and we will go into energy considerations. We are going to find out how from energy considerations we would be able to obtain additional information of the variation of temperature with position or with r. Ultimately, the goal is to obtain an expression which is equivalent to that of Newton's law, that is Q is equal to H A delta T. Now, we understand what this delta T is going to be. This delta T is going to be T of the surface minus T m, where T m is the mean temperature of the fluid. For the case of constant surface heat flux, this T s is a function of x. For constant surface temperature, this T x is going to be a constant. So, how does this change? That T being a function of x, T s being a function of x and T s being a constant would give me slightly different relations for the heat transfer, for the convective heat transfer, fundamentally they are the same. Fundamentally we would still get an expression of the form Q equals H A delta T, but you would see that the way it is defined, the way we are going to get the final expression would tell us something about the temperature difference to be used. So, why is this difference? Let's think of a tube and a flow is coming in at some temperature. So, when it enters, there is a certain temperature difference between the two. So, the surface is at some Ts and the liquid which is coming is at Tm. So, the gradient is Ts minus Tm. As I move in this direction, then my Tm will change, my Ts may also change if it is a surface condition. So, the gradient, the cause which accounts for convective heat transfer, which is Ts minus Tm, can also be a function of x. So, if I have an inlet and an outlet, at the inlet the temperature difference is Ts at I minus Tm at I. At the outlet it is Ts at O, that is outlet, and the temperature is Tm at O. So, the root cause for convective heat transfer, this keeps on changing between the inlet and the outlet. So, if I would like to express everything on an overall sense, what should be the expression for something which is similar to Newton's law, that would give me an average heat transfer coefficient, express the total heat transfer from the wall to the fluid over a certain length L. I would like to know the total heat transfer. So, Q, not the prime, Q is H A delta T. So, what this H is going to be and what delta T I should use, since my delta T is a function of x. That is what we are trying to do next for the case of constant surface heat flux condition and for the case of constant surface temperature condition. So, starting with an energy consideration, we are going to look at these, we are going to derive these two expressions. That is what I am going to do next. So, in order to do that, I am going to start with an energy balance of the liquid which is coming into the system. So, when I talk about the energy balance between the flow which is coming in and the flow which is going out, the differential amount of energy dq convection which comes into this must be equal to mCp dTm. So, whatever be the change in the mean temperature multiplied by mCp, and we assume that the thermophysical properties which are embedded in m dot, that is rho and Cp, are constant over the temperature range that we are considering over here. So, this is from this this comes directly from conservation of energy. So, if we do the integration over the length, so that we would like to find out what is the total amount of heat Q convection that is being added to it. So, one can simply write Q convection is going to be m dot Cp Tm at the outlet minus Tm at the inlet. So, your energy conservation simply gives you a standard very basic relation between the heat that comes in. So, this is convection and the wall. Now, when I talk about a circular tube, what we would get is dq convection. This is when I am considering the flowing liquid. Now, I am considering, so when I consider the tube, the element of fluid as it moves in this direction, if I consider between 2 points, this gives me whatever be the total energy content over here and the total energy content over here. So, this minus this gives me the amount of energy which is being added from the side walls, but the amount of energy which is being added from the side walls can also be obtained by Newton's law of cooling. So, what is that going to be? So, dq convection would simply be q double prime s, the surface heat flux, times P into dx, where P is the perimeter. So, that is a differential form of the that is just a differential form of the convective heat which is being added, which depends on the Qs, where Q double prime S is the local value of the surface heat flux, P is the perimeter, and dx is the elemental length. So, in this, for the case if I consider this is a circular tube, then P is simply going to be equal to pi times d. So, dTm by dx therefore, simply going to be equal to q double prime s times P by m dot Cp. Okay. So, the variation in temperature with x can simply be obtained if you see this one and this one. I simply have combined this equation with this to obtain dTm by dx is equal to q double prime s times P by m dot Cp. So, this can be, this one is now I am going to express in terms of Newton's law of cooling. So, it is going to be P by m dot Cp times H Ts minus Tm. So, this is simply from the conservation of energy which is over here and the amount of heat that I am adding by convection through the sides, P the perimeter, and dx is the elemental length. So, if I do that, then I can find out what is the axial variation of Tm can be obtained from this relation. So, we also should note that generally P m dot Cp are constants, and if I assume that it is fully developed, thermally fully developed flow, then my H is also a constant. Okay. So, this is what I am definitely going to get in the terms of H is a constant, surface constant, H is going to be a constant. Now, I am going to write this equation for the case of constant surface heat flux. So, the first condition that I am going to use, I will write this expression once again over here, that is dTm by dx is equal to P by m dot Cp from previous page H Ts minus Tm. This is the expression which we have obtained, and we would like to use it for constant surface heat flux. So, that means your q double prime s is a constant. So, q convection, if I consider over here, my total q convection would simply be q s double prime times P into dl. Since this is not a function of x anymore, if I integrate on both sides, this becomes my q convection, q s and P can be taken outside of it, and simply I am going to get P times L. So, for constant surface heat flux, my starting point would simply be dq convection is equal to q double prime s P dx. So, once I integrate this, these two are outside of the integration sign. So, my q convection, which is this, would simply be equal to q double prime s times P, and this is 0 to L. So, it should simply be, this should simply be q times P L. So, therefore, from here I can now write my dTm by dx to be equal to P times q double prime s by m dot Cp. And if you look at this expression here, then this is not a function of x. My perimeter is constant, my heat flux is constant, m dot and Cp all are constant. Therefore, my variation in the axial temperature difference, variation in the mean temperature, actual variation in the mean temperature is not a function of x. So, I can integrate this to obtain T m, which is a function of x. So, the mean temperature as a function of x can be obtained from here, which is T m I, whatever was the mean temperature at the inlet plus q double prime S p by m dot Cp times x. So, this simply tells me that for the case of constant surface heat flux, mean temperature of the fluid varies linearly with axial position. Where x is the axial position. So, this is an important result. So, we are looking at first condition where it is a constant surface heat flux, and a constant surface heat flux with this definition I simply obtained this dTm dx to be a constant. So, my mean temperature of the fluid varies linearly with x, that means with the axial position. What is left, what I am going to do in the next class is for condition 2, when the surface temperature is kept constant, and I would like to see how can I express T m, the temperature, mean temperature of the fluid, actually what would be the functional dependence of T m with x for the case of constant wall temperature. So, that is the second case which is remaining, which we are going to do in the next class. So, the summary of today's class is, from an energy consideration we are trying to obtain the variation of the mean temperature of the fluid as a function of different parameters for the cases of constant surface heat flux and for the case of constant surface temperature. And we would see in one case it varies linearly, which is the case of constant surface heat flux, and we will examine what would happen when the temperature is kept constant, which we will take up in the next class.